Today we're going to talk about OpenCL events and how we handle events. Event is an indication when an OpenCL operation occurs. Event is a data structure that corresponds to an occurrence. Event can be used to monitor the operations in the OpenCL framework. It can be a host notification to notify the host that a command has completed on a device. It can be also used to synchronize commands so that we can force commands to delay their execution until another event takes place. We can also use events to do profiling, that is to monitor how much time a command takes to execute. It is very useful for performance evaluations and optimizations. Host can send commands to a device through its command queue, then to execute the kernel, to transfer data, to map device's memory, etc. After we enqueue the command, the host has no control over how the commands will be executed. However, host can receive notifications when command completes its execution by using this CL event data structure. Callback functions are very useful to transfer information through events. Let's take a look at this example. To transfer data from a device to a host, we can use CL enqueue read buffer. To avoid waiting, we can use non-blocking read by setting the third argument of this CL enqueue read buffer as CL false. Then host can perform other tasks as CL enqueue read buffer returns immediately. And to allow host to respond when the data transfer is completed, we can associate an event with the data transfer command using an event argument. And also we can associate the event with a function to be called on the host, and this is the callback function. We can use callback functions as follows. Let's assume that we have an enqueue task API that's called, and we use this EV as the event that pass into this enqueue command. And then we can use CL set event callback to associate the callback function with a particular event. This CL set event callback takes a few arguments. The first one is the event that we want to associate the callback function to, and then the callback type, and then the function pointer to the callback function. Callback type can only be CL complete because we only trigger the callback function when the command reaches to the complete status. For example, in this case, we can say CL set event callback EV, which is the event we declared and associated with this enqueue task API, and the callback type is CL complete. Then process is the entry point of the callback function, and we do not pass in any data, so that's going to be null. All the callback functions use the same signature, so it is void CL callback with the function name, and then takes three arguments: the event, status, and then the data. Here's the complete example. We first declare the callback function as void CL callback, the name of the callback function as process, and then we take three arguments: the event, the status of the event, and then data. In this case, we use data to pass in any reference to the parameter data. And in the main program, on the host, we'll declare the event EV, and then we declare a message, hello world, and then we can use CL set event callback to associate this callback function process with the event EV. And this MSG is, for example, we use this MSG to pass in any parameters that might be necessary to this callback function. Here's another example. We declare another callback function, kernel complete. And again, it takes three arguments: the event, the return status, and any parameters that this callback function might need. In this case, it's data. Also, we declare another callback function. It's called read_complete. Similarly, it takes 3 arguments. And in this callback function, we will go through the data by using this pointer. And then the buffer data points data that we pass in to this callback function. And then we go through the buffer to check if there's any data in this return data that has a value that's not equal to 5.0. And if that's the case, we say that's an error, and then we break. And so overall, this callback function is to check whether the data has been initialized to 5.0. And this is the host side main program. We declare several arguments. We declare several variables: kernel message, character, array, and floating point buffer data. And then we have a memory object called a data buffer. And then we have 2 events: kernel event and read event. First, we do CL enqueue task. This is essentially create a very simple kernel that executes only 1 work item, and it takes kernel argument as the last argument. So that is associate this command with this kernel event. And this is non-blocking. So this CL enqueue task will proceed because we don't have to wait for any other events. And then we execute CL enqueue read buffer, which takes a few more arguments: the command queue, the data buffer, which is the memory object, and it's non-blocking, and we pass in the data and also the size of data, so we know where we want to put the data to on the host side. And then we'll associate this command CL read buffer with this read event. Next is to initialize the kernel message. So we put this message into this kernel message buffer. And then we set the callback function using CL set event callback. And in this case, we associate this kernel complete callback function with this kernel event. And we pass in the kernel message as the argument to this callback function. And we do some error checking to see if this callback function is set up properly. Similarly, we can set the callback function for the read event to set this read complete function as the callback function for read event. And finally, we release the events. Now, note that this CL event callback should be called after enqueuing functions, because by the time we set this callback function, we assume that this event is already associated with some certain commands, like we did here. So when we call this callback to set the callback function for this kernel complete, this event, kernel event, has already been associated with this kernel enqueue task function. Command synchronization events. By default, a command queue processes commands in the order they are received. So by default, that is the in-order execution of commands. And there's no way to tell the order of actual execution if the commands are dispatched to different command queues in a context. If you want, you can establish your own order of commands execution by using waitlist. Waitlists are very useful to delay one or more commands based on your need. The command event is associated with a command, and user events are associated with an occurrence within a host program. Waitlist and command events are the ones that we use to set up certain dependency orders for the commands. If a command's waitlist is null, you can start executing as soon as it reaches to the end of the command queue. Otherwise, a command must halt until for every event on the waitlist to occur. For example, if we have 2 kernel events, and these 2 kernel events are associated with this enqueue task and this enqueue task respectively. So this kernel event 0 will be triggered when this first enqueue task is completed. Likewise, this kernel event 1 will be triggered when the second enqueue task is completed. The third enqueue task which takes two events on the wait list, and these events are on this kernel event list. So that is to say, the third in-queue task, this particular command, will hold until the first two commands have completed, because we are waiting for the events on this list, and we're waiting for both of them. And the third in-queue task does not generate any task upon its own completion, because in the future there's no need, in this case, to wait for this third event. There are some differences between command and user events. Command events correspond to the commands executed on the devices, whereas user events are generated by the host application. With a user event, you can also stall a command's execution from the host, but not on the device. You can use CL create user event to create such user event. In this case, you do not need to associate the event with a command. You don't need a command queue as the argument. Instead, this CL create user event takes only two arguments. The first one is context, and the second one is the return error code. If you add a user event to command's waitlist, the execution of the command will halt until the host application updates that user event's status. And to do that, we use CL set user event status. And it takes the event as the first argument, then the status as the second argument to change the event to. And the second argument is, in fact, can only be set to CL complete. If the status is to set to a negative number other than CL complete, then all the commands waiting on the user event will be terminated. We have another example here. The first is the callback function we declare. It's called read complete. In the main program, we declare several events: user event, kernel event, and read event. And then we use CL create user event to create such user event. And then we call CL in-queue task. And we take the user event on the wait list, and we only wait for that one user event. And because this user event is just being created, so the status has not reached to CL complete. This CL in-queue task actually going to make the command hot, not putting the kernel into execution, because the events on the waitlist has not reached complete status. And this CL in-queue read buffer will proceed to send a new command to the command queue to prepare for reading data from the buffers. And because this CL false is set, so this read buffer API will proceed, but the actual read operation will not start until this kernel event is triggered. That means until the kernel event is turned into CL complete, the read operation will not proceed. And then the next line is to set event callback. So we are setting the read complete as the callback function for the read event. And then finally, we'll wait for 1 second. So we just print out the initial values in this data buffer and wait for user input. At this point, none of these commands are actually being executed, even though they have been put into the command queue. So in other words, this in-queue task, which is supposed to start a work item as the kernel function, will not be executed because it has been waiting for the user event. Also, the actual read operation on the buffer has not started because it has been waiting for this kernel event, which has not happened yet. And the next line of code is to set user event status to change the status of the user event to CL complete or CL success. And then at this point, this CL enqueue task will eventually execute the kernel, and then which subsequently will set this kernel event to be CL complete. And up to that point, the read operation, the read command has been waiting. So when it sees this kernel event is turned to CL complete, then read operation will proceed because this kernel event has become CL complete. And once this read operation is completed, then this read event will be turned into CL complete, and then this CL event callback, because we set up the CL complete as the callback function, so the read complete function will be called. Now the question we have here is, what if we set this blocking flag to be CL true? Well, if we set this CL true as the blocking flag, that is to say, this API will be set to blocking. As a result, the following set event callback will not be executed because the host program will be stuck here waiting for the kernel event. And subsequently, this CL set event status will not be executed. So this host program will be stuck here forever. We can use CL get event info to access information about the event, such as context, command queue, type of command. So the API is as follows. CL get event info, you put the first argument as the event, and then you specify the parameter name you want to query about the information, and then you specify the value size and the actual value. The parameter names can be CL event context, the command queue, execution status, which will return the status of the corresponding command. For example, CL queued, CL submitted, CL running, or CL complete. And most often we want to use CL complete because that's a status of a command which can trigger subsequent operations. The status of a command can be in one of the 4 stages. Queued. The command is placed into the command queue. And then submitted. The command is then submitted to the device. Running. The command is being executed on the device. And finally, complete. The command's execution has finished. CL set event callback and CL set user event status will only work properly for the CL complete stage. Let's look at this example. We have a callback function called getQueue. And in this callback function, we'll call get the event info. And then the other callback function is to get type. And in this callback function, we use CL get event info to query the command type and then determine what we do with these specific type of commands.